For the wind-up car, we have a little physics problem for you. From experimenting, you'll probably see that the smaller wheels allow the car to go up steeper slopes. But in this problem, we would like to calculate the maximum slope that the small wheels can take the car up versus the maximum slope that the big wheels can take the car up. In the problem, this is the free body diagram that we are given with. This is the angle of the slope. We name it theta here. And this is the drive wheel, and there is an applied torque acting on the wheel. This torque originally comes from the spring that we wind up and is transferred to the drive axle. And for all the forces acting on the drive wheel, we have the gravity force, which is basically the weight of the car. And next we have normal force, which is acting on the wheel from the ground. And finally we have traction force. Traction is the force that is basically pushing the car to go up the slope. Let's look at the first hint. The first hint is talking about torque. So let's review what torque is. Torque measures a force tendency to cause a rotational motion around a pivot point. Torque is equal to the force times the perpendicular distance between the force and the pivot point. In our case, we are going to choose the center of the wheel as our pivot point. And we see that there is no torque generated by the normal force because the normal force is going through the pivot point. It's the same with the gravity force. Because it's going through the pivot point, it is not generating any torque. For traction force, we have torque generated by it. Torque from traction is equal to traction times the perpendicular distance, and that is basically the radius of the wheel. And the direction of the torque generated by traction is counterclockwise, which is in the opposite direction of the applied torque. In order for the wheel to keep rolling forward without angular acceleration, the two torques have to equal each other. This is basically what hint 1 has told us. So we write out that applied torque is equal to traction times wheel radius, and this is going to be our first equation that we are going to use later. Now we're going to take a look at hint 2. It tells us to break down the Fg force, which is the gravity force, into its component. So we are going to break down the gravity force into its convenient axis, and in this case, the two axes are parallel and perpendicular to the slope. And from geometry, we know that this angle is also theta. Let's write the gravity force here. From trigonometry, we know that the top component is equal to Fg sine theta, and the other component is Fg cosine theta. In order for the car to be able to go up the slope, the traction force has to be higher or equal to the component of the gravity force that is pushing it down the slope. And we can write that out as traction is greater or equal to Fg sine theta. This equation tells us that there are many thetas where traction is great enough to pull the car up the slope, but we are looking for the maximum theta here. So we get the equation traction is equal to Fg sine theta. And this is the second equation that we need in order to solve our problem. Let's start with the big wheel. From equation 1, we can calculate that the traction generated by the big wheel is equal to applied torque over the big wheel radius. And from equation 2, we know that traction is equal to Fg sine theta. And we denote this theta with a capital R subscript because it is the maximum angle of the slope that the big wheels can go up. And because Fg is gravity force, we know that that is mg, where m is the mass of the whole car in this case, and g is the gravity. So we can write that traction from the big wheels equals to mg sine theta capital R. Rearranging the equation, we have applied torque is equal to mg sine theta capital R times the radius of the big wheel. Very similarly for the small wheels. Using equation 1, we write traction for the small wheel. We denote that by using the lowercase r subscript here. That is equal to applied torque over the radius of the small wheel. And using equation 2, it is equal to Fg sine theta lowercase r, and we use lowercase r for this theta because it is the maximum angle of the slope for the small wheel. Just like before, we have the traction equals to mg sine theta lowercase r. Rearranging the equation, we have applied torque is equal to mg sine theta lowercase r times the radius of the small wheel. And we know that the applied torque is the same in both cases of the big wheel and the small wheel because the applied torque originates from the same torsion spring. So we can write that mg sine theta capital R times capital R equals to mg sine theta lower r times lower r. And we can cancel mg on both sides. And rearranging, we have sine theta capital R over sine theta lower r equals to lower r over capital R. And this is our answer. And don't forget to confirm your calculations by running actual experiments.